Behind me, I have a question from the International Mathematical Olympiad, IMO for short. It's from the year 1995, and it's the last problem. The problem statement is as follows. Let P be an odd prime number. How many P element subsets A of 1, 2, all the way to 2P are there, such that the sum of the elements is divisible by P? Now, this is a really beautiful problem because even though it's a counting problem, you have to use an algebraic device and complex numbers to solve it. And as you might have guessed, that algebraic device is called the generating function. However, the main difficulty of this question is actually this part. P elements. The subset must contain exactly P elements in it. So how do we get a generating function to track the sum and the number of elements? Like, how do we do that, right? I mean, if this condition was not here, then we could just simply use the generating function f of x equal to 1 plus x times 1 plus x squared times all the way to 1 plus x to the 2p. And that's because each binomial, 1 plus x to the k, represents a binary choice of not including k or including k within the subset. But this has no way of tracking the number of elements within your subset. So what can we do? Well, consider this function. Consider the function f of x, y, taking on two variables, and we're going to define this to be equal to 1 plus yx times 1 plus yx squared times all the way to 1 plus yx to the 2p. So, why is this function relevant? Well, consider this. Notice that if you were to expand this entire polynomial, then each term will look something like ams times x to the s times y to the m. Now, notice that this y term keeps track of the number of elements within the subset. Because each time you decide to choose an element to be included within the subset, this exponent on y will increase by 1. So this m actually tells you the length of the subset. And this x term keeps track of the sum because, well, this s over here keeps track of the sum, right? Now, this coefficient of ams tells you how many ways are there to achieve a sum of s with a subset length of m. So that's the idea behind this generating function. Okay, so let's proceed with it. Notice that the problem conditions, well, they basically ask us to find the coefficients of the terms where x is raised to some power, d1, where this d1 is divisible by p, and it must also have the term, it must also be multiplied with y to the p, because we must have the subset length to be p elements, exactly. So we must filter out both of these conditions. But it's not very easy to consider both of them at the same time. So let's just focus on this one first, okay? This x to the d1 condition first. Then we'll worry about the y condition. Okay, so I have denoted our conditions over here. We're going to first focus on condition number 1. So how do we extract all terms in which we have x to some power, where that power is divisible by a prime? Well, there's actually a very nice formula for this. It's called the root of unity filter. Basically, if you have a function g of x, and this function is a polynomial, so it's equal to the sum as k goes from 0 up to n of ck times x to some k. So basically, ck is the coefficient, right? If you have this polynomial and you wish to find the value of c0 plus cm plus c2m plus c3m plus ... Basically, this sum is the sum of c sub some multiple of m, right? If you want to find this sum, then there's a really nice formula for this. If you let omega equal to e to the I 2 pi over m, then this sum is just equal to g of 1 plus g of omega plus g of omega squared plus dot 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 all the way to g of omega to the m minus 1, and then divide by m. This is a formula to extract all the relevant coefficients divisible by m. So we're going to condense this because this is taking up a lot of space. We're going to write this with a summation. This is the formula to extract the relevant coefficients. So I know this looks complicated, but this is going to be super helpful for this first condition and the second condition as well. Now we have our formula over here. Note that the relevant case is when m is equal to p for our question, right? Now notice that with this formula, if we were to treat y as some constant, then we can use the roots of unity filter to find all x terms in which the power is divisible by the prime, right? So let's use the formula. Basically, this formula gives us f of 1y plus f of omega y, yes, omega y, plus f of omega squared y, plus all the way to f of omega to the p minus 1 y. And we have to finally divide this entire thing by p. So this function has only the x terms, where the x is raised to some power divisible by p. The y is still left untouched. We left it as a constant. We treated it as a constant, right? We're going to filter that out later, but as of right now, we've achieved our goal for x. We just need to evaluate this because this does not look pretty. Okay, starting off with f of 1y. Notice that if you were to plug in x for 1 in each of them, well then, f of 1y, this becomes 1 plus y to the 2p. Okay, the rest of the sum. Notice that omega is a primitive pth root of unity, and omega squared is also a primitive pth root of unity, all the way to omega to the p minus 1, all primitive pth roots of unity, because p is a prime number. What does that mean? Well, that means that each of these terms are all equal in terms of y. Why is that? Well, recall that primitive roots of unity, if you raise them in successive powers, they become the same thing as the set of the original roots of unity, just reordered. So, in fact, all of these are the same, we just need to calculate one of them. Let's just calculate f of omega y. If you plug in x for omega, you would get 1 plus y times omega times 1 plus y times omega squared times all the way to 1 plus y times omega to the 2p. And because there are p of these added together, we have to, well, not p of them, there are p minus 1 of them being added together, we have to multiply this by p minus 1. And then we still have this division by p at the bottom. Okay, now we have a function in terms of y. But first, let's just name this function. Let's just call it h of y. Okay, so we're now going to direct our attention to h of y and filtering out the relevant y terms. Okay, so we have our h function over here, and I've used the pi notation to condense our product. Okay, so remember, our goal is to filter out all terms with y to the p. So basically, we want to find the coefficient of y to the p, or CP. However, if you pay attention to the roots of unity filter formula, notice that it starts from C0, and it's like a sum of successive terms. This is just one term on its own, so this does not apply. But don't worry, all is not lost. Consider this. When we have y to some power, where this power is divisible by a prime, how many possibilities are there for that? Well, very little. Notice that y to the 0 is one of them, right? 0 is divisible by p. Another possibility is y to the p, and also y to the 2p. And this is the maximum, because you can only ever have a maximum of 2p elements in a subset. So these are the only 3 possible degrees we have to worry about. So if we apply roots of unity filter for these 3 powers, then we're good. And notice that there's only one possibility for an empty set, and only one possibility for the subset to be the entire set as well. So once we apply roots of unity filter formula, all we need to do is subtract our result by 2. So let's do that. by this formula, we have that C0 plus CP plus C2P, basically the coefficients of these terms, the sum will be equal to, well, by this formula, 1 over P times the sum as j goes from 0 up to P minus 1 of h of omega to the j. Basically, this omega definition, along with this, still remains. So let's evaluate this. We can distribute the summations once we make the substitution for h, which is going to be pretty long, so bear with me. So this is equal to 1 over p, and then times, notice that this 1 over p can be taken out of the entire summation. So that's 1 over p squared times the summation of j going from 0 up to p minus 1 of 1 plus omega to the j of 2p. And then plus, again, this p minus 1, that's independent of the summation. You can take it out. P minus 1 taken out. And that's going to be the sum as j goes from 0 up to p minus 1 of the product. This is why I used the pi notation. Otherwise, I would take up literally the entire board. And this y over here, by the way, is omega to the j. And the exponents add, so this becomes omega to the j plus k. This is what we have. We need an extra bracket. So this is what we have over here. Okay, now we have to evaluate these two pretty terrifying looking summations. But the truth is that they actually have pretty well-known values, or even if you don't call them well-known, they do have pretty well-known algorithms in which you can use to compute them. So I'm just going to skip to the point and write their values down. If you are really interested in seeing a proof, then please see the pinned comment down below. I will be leaving links to the explanations there. They might not be out yet. I might still have to, take time to film them. But if they are, then check them out. So basically, this entire expression is equal to 1 over p squared, and then times this summation, a well-known value, is equal to p times 2p choose p, and then plus 2p. And then we have plus this p minus 1 over here. And this summation over here, can you guess what it is? Well, it's just equal to 4p. So simple, right? Definitely check out the proofs if you're interested. So we just need to distribute this p squared in, 1 over p squared rather, and then we just need to simplify the entire expression. I'm going to skip the simplification. This will be equal to 2p choose p minus 2 over p, and then plus 4. Now, this is the number we are looking for. But remember, you have to subtract these two cases that are not valid. So subtracting 2 from this, well, it would be no longer equal to any of this anymore. But subtracting 2, you would get this as our answer. So this entire expression is our answer to the IMO problem. I know this problem had some abstract concepts, but you don't have to understand everything to learn something. Even if you just understood the very first generating function that we came up with, remember that f of xy function? If you just understood that, then you learned something, which is pretty much all that matters from this problem. The point of studying these contest problems isn't to just get the answer, is to learn some new concepts. So if you did learn something new, then congratulations. And as you can see, a very beautiful problem indeed. So anyways, I hope you enjoyed this video. I hope you found it interesting. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.